when we finish class, I will post on YouTube. Yeah, and Sutipong, my assistant, will send email to you to share link of YouTube. You can suggest your student to learn to review.
Okay.
Yes.
Okay.
Yes.
Sure. Sure.
So much.
Sure.
And I have another assistant, Mr. Pirapat. For class today, I assign 3 students to attend. Yes,
All
you
right.
for my assistant, but my graduate student in my faculty, I think around 10, around 10. Yes.
Around 10. Okay.
Yeah.
All right. All right. Sure. Sure. I invited around 3 or 4 students.
Okay. Okay.
I hope
Yeah.
they will attend the class.
Okay. And Professor, for this class, we have 2 sections. Section, morning section and afternoon section.
Afternoon section.
Yeah, yeah, and you can follow your presentation, your slide. And then if I have time, I will visit class. And sorry again for my time.
No worries. It's okay.
And
It's okay.
if possible, you please try to visit Thailand.
Sure, I will try. I hope to visit Hanyai too.
Yes. And if you visit in Chinese season, Chinese festival or something, we have Chinese fair. I think you love to eat Hat Yai Chinese food. Yeah. I'm not sure similar your country or not for Thai foods and Malaysian food.
There are some similarity, but also different.
Yeah, yeah. I never eat Malaysian
food.
Yeah. Okay. I need to assign you as co-host for this class.
Okay.
I make you co-host and meet Pirapat host. Okay. Okay, Professor. I will open the class. Good morning, student and coming student. I'm Dr. Isara Chanakel Sambun from Faculty of Environmental Management, Prince of Songkhla University. Today, I would like to introduce Associate Professor Dr. Jack Kie Cheng from Faculty of Industrial Management, University Malaysia Pahang, from Malaysia country. Professor will talk in the topic of sustainable industrial management using simulation arena simulation software for our students. So I would like to invite our students to concentrate for the class. And if you have any question, please ask her because Professor she very kind can help you. Thank you again, Professor.
Thank you, Dr. Isara.
Thank you. And you can start class now.
All right, sure. Thank you so much. So I will start with my slide. So thank you to Dr. Isara for such a nice introduction. So thank you also for the invitation for me to talk about sustainable industrial management using simulation. So I am Jackie. I am from Universiti Malaysia Pahang. And this is a little bit background on me. So I did my PhD and bachelor degree in decision science from Universiti Utara Malaysia, and I just Googled just now how far Universiti Utara Malaysia. Universiti Utara Malaysia is at the northern side of Malaysia, and I tried to Google the distance from UUM to Hat Yai. So it's around 1.5 hours. So my alumni, my alma mater actually is quite near to Hat Yai. And currently I am servicing in the Faculty of Industrial Management in Universiti Malaysia Pahang, which is over the east coast of Malaysia. So my area of interest includes building simulation models, and also I like analytics, and I also have much interest in the topic of operations research and also system thinking. So I also put some of my pictures with students, see when they are happy in the class and joyful in class, so that actually motivates me to be more happy in preparing my lecture. So I hope all of you will be able to follow through the class today. So I will start with the class plan or the lecture plan for today. So there will be two parts. The first part, we will talk about the introduction to simulation, which will happen from 10 o'clock to 12. And then we will have a short break for lunch from 12 to 1. And coming back after lunch, we will straightly jump to explore Arena simulation software. So the first part of our class will be more on understanding what a simulation, the description of simulation, the types of simulation, and what is actually simulation. And after lunch, we will have some hands-on. We will start to learn or start to explore one of the simulation software, which we call it as Arena. So I guess we will have a few students joining online via this Zoom session. So if you have any questions, please stop me anytime. All right, so with that, I will start the first part of our class today, which is to talk about what is simulation. Yeah, so this is the first part, an introduction to simulation. So I hope all of you have a rough understanding on what is simulation. So if you have some confusion in any part of our discussion, please feel free, don't be shy, you can stop me anywhere. Right, so we start with the big word simulation. So what does simulation actually means? So simulation is the process of designing a model of a real system. So let's have like 3 seconds to digest the sentence. Simulation is the process. It's a process of designing a model of a real system, meaning that we have a real system and we try to build a model out of the system. So you might have a bit of confusion, what is a model and what is a system. So let's look at this example. So if we can see an example here, so this is not a real human. So this is a model of a human which shows all the organ of a human. So this is a model. So the next picture is actually a real human. So it actually represents a system, because in human, we have so many different kind of system in us. We have respiratory systems, we have digestive system, nervous system, cardiovascular system, so on and so forth. So this is a system. A real human is a real system. And if we look at this example, this is actually also a model. So it is not a real human, but a model or an imitation of a real human, where you can use this model to further understand more on the human body. Okay, so from these three pictures, we can actually say that system is the actual thing, while model is actually the imitation of a system. Model is an imitation or a smaller section of the real thing, which is the system. So let's go a little bit further. So we have an answer here. So system, by definition, is a facility or process, actual or planned. So the keyword here is system is the actual thing, and model is a set of assumption, approximation on how a system works or how a system functions. All right, so that's before we proceed to the examples related to the industry. So when we talk about systems, usually people tend to think system as computer systems, but actually a system is more than computer system, like what we talked about earlier on, where human body itself consists of so many different kind of systems. And also we have the solar system as well. And if we want to put systems in the context of an industrial, so we can have an example like a bank. A bank itself, it's a system with many different kinds of customers. So you have customers coming in to deposit their money, bank in their money, or trying to apply a loan, and so many different kinds of customers depending on what are the services that the bank offer. And then besides having customers, the bank also have servers, facilities like teller windows, like the ATMs, loan desk, safety deposit boxes, so on and so forth. So bank itself is a system by itself. So if we want to imagine a bank as a model, how does it look like, or how will it look like? So I actually prepare a video which we can see. All right, can you see the video? Can you see this video?
Yes, we can.
Thank you so much. So this, let me start from the beginning. So this is actually a model of a bank operation. So what we can see here is a model is an imitation of the real system, and we actually create the entire operation of a bank in the model. So depending on the bank that we are trying to simulate, we will simulate exactly the same number of counters, the same number of staff. The entire layout of the bank, we will actually put it into a simulation model. So you can see here, we have on the top, we can see all the counters, the bank officers on desks, and then they have their managers right at the back. And then we have customers being served. And then we have at the lower part, we have the chairs for customers to get their number and sit while waiting for them being called and being served. And then we also can see on the left-hand side, there are a few ATM machines. So it's actually mimicking the actual bank operation. Right, so let's go to the next one. Apart from the bank here, we also have this manufacturing plant. So a manufacturing plant itself is a system. So a manufacturing plant, regardless of what it's manufacturing, whether it's manufacturing a car or tables or food or anything, so it consists of machines, people, transport devices to transport the parts from one conveyor to another conveyor, and of course we have the conveyor belts, and then we also have the storage space or the warehouse for either the finished goods or the raw materials. So manufacturing plant itself is a system. So if we can look at an example of a model of manufacturing plant, let's look at this. So again, this is an imitation of the actual manufacturing plant. So you have the conveyor belts transferring the goods from one part to one part, and it's being processed. Okay, let's go to our next example. So apart from the manufacturing plant, we also have an airport. If any of you have traveled or have been to an airport, you can have the rough idea on how complex is an airport. So an airport with departing passengers checking in, going through the security, going through the departure gate, and then boarding, and then departing flights. We have departing flights, arriving flights, and then we have arriving crews, arriving passengers, and then not only passengers, and then their baggage as well, where to wait for their baggage, and then if their baggage got lost around the route, what to do, and then if there's equipment failures, what happened. So airport itself, it's a very complicated system. So let's look at an example of a model of the airport. So from here itself, when we look at the model, we can actually have a rough idea on how the airport is actually operating. So usually in a model, we have like a small what we call this, a small indicator here to indicate some figure. How many passengers are currently in the airport, each lane, how many customers are in each lane, and then all of their counters, how long is their queue, so on and so forth. So this clearly shows the movement of passengers in the airport, right from the arrival moving to the gates, and then from the departure, so on and so forth. So what we see now, we already see like 3 different types of models, and all these 3 models are developed using different simulation software. So we have Simio, we have FlexSim, the banking model just now, and then we have the first one. The first one is using Arena, the bank, and then the manufacturing plant model is using FlexSim. And now for the airport, they are using Simio. So in the afternoon, after our lunch break, we will explore more on Arena software. All right, so let's go to our next example. So in our next example, let's see what we have. So we have healthcare. So healthcare or a health center is a system with its complexity. So if we just take one part of the complexity of a hospital, if we look at emergency facilities, so it's, of course, we have nurses, doctors, we have different rooms, different equipments, different supplies, and then different kind of transport, different types of mediums to transport the patients from one place to another. Right, so let's look at a video which portrayed the model of a hospital. Right, So I actually look for a simulation model of a vaccination clinic. So we all just gone through the COVID-19 pandemic. So during the pandemic, we have in Malaysia we have a few centers where this centers or this clinic give a vaccination. So for this researcher, he or she actually simulate what is the best layout if a center or a stadium is being converted into a vaccination area or vaccination clinic. So they actually simulate it and see whether it's possible or not to do so. And what are the potential issues that will arise if converting a stadium into a vaccination center. So we can see I'll fast forward a little bit. And behind the animation that we saw just now for all the 4 examples, at the back of this animation, there are something that we call it as a model logic, where we will build the process of the operation beforehand. So once we successfully build all this, and then we will actually build the animation on top of this process. So for this example, this researcher is using AnyLogic software. So for simulation itself, or simulation model, there are many different types of software available to construct a simulation model. So that will depend on what type of simulation that we are using. So all those things will be covered in our next, I think next 45 minutes. Okay. All right, so I'll go back to my slide. All right, so if we can do a little bit of recap, simulation is the process of designing a model of a real system. So we have a real system, be it a hospital or a bank or a factory or a supermarket. So we try to design a model out of that system. So this process is called simulation. Okay. Apart from all the examples that I showed just now, so highway itself or roads, highways is actually a very complicated system. So now you might think or you might have query on, so why do we want to build a model of a real system? So what is the reason for us to come up with a model? Why can't we just interact with the real system? So the reason for us to model the entire system or the real system is to conduct experiment with this model. And why do we need to conduct experiment? There are 2 reasons. The first one is to understand the behavior of the system. Is the system currently operating efficiently or not efficiently? What is the current state of the system? So that is the purpose of a model. We are trying to understand the behavior of the system. Secondly, we would like to evaluate different types of strategy. How can we further improve the operation of the system? So in short, the reason for us to actually build a simulation model of a real system is actually to conduct an experiment with the model with the hope of understanding the behavior of the system to see whether the system is currently operating efficiently or not. And if it's not efficient, how can we improve the efficiency or the performance of the system? Let's see. So this is the rough definition of simulation. On the right hand side is the definition that we just discussed earlier. So if you find the definition on the right hand side is a bit lengthy, then you can look at the left hand side, which is a definition that I get from Wikipedia, which is much shorter. So in short, simulation is an imitation. Yeah, the key word here is imitation. Imitation of the operation of a process, be it emergency room process, or it's a supermarket process, or a process in the factory, or a system. Imitation of this process and system that represents its operations over time. Yeah, so basically it's just an imitation of an actual system. So why do we want to imitate the system? Because we want to conduct experiment to understand the behavior of the system and to actually find ways to improve. What are the best strategy to improve the performances, the processes of the system? So that is basically the definition of simulation and also the function of simulation. All right, so why should we work with the system? Right. So systems, we need to work with system for these four purposes. The first is to measure the performance. Is the system is working well? Is the queue in each of the processes is lengthy? And then after we measure the performance, we will able to know which process in the system needs to be improved. So that goes to the point number 2, which is to improve the operations. And beside improving the operations, we also want to design a new process if it doesn't exist. And also we want to control if there's any breakdown. Let's say the breakdown of machines, breakdown of staff, breakdown of resources. So what should we do when there are those breakdowns? So we can actually try it in a simulation model, test it, and try different scenarios and see the impact before actually implementing it into the real world. So why work with system again? So sometimes working with system, like what we mentioned in our previous slide, to achieve all these 4 points, but sometimes it's a challenge to work with the system. Because if we want to do all testings, let's say we want to improve the performance of a road. Let's say we have a road in your city where it's so congested early in the morning or late in the evening. So we thought of a way to improve the roads, the roads, and it's actually very costly to directly change the road. So if we directly change the roads, like we change the setting of the traffic lights, or we change the 2 direction of roads into 1 direction, if we actually implement all these changes to the real road, we all can imagine that it will actually create even more congestion, and it's more dangerous to the people using the roads, and it may cause accident as well. So that's why it is more safer actually to conduct all these changes in a controlled environment like a simulation model. So like here, I also put 4 examples here. So we can actually experiment with alternative layout of a factory that has not been built. So let's say we want to propose to build a new factory and also with a different layout of the factory. So it's hard for us to actually experiment it physically because the factory is not built yet. So we can actually do so in a simulation model. And again, if in an existing factory, it is very costly to change the layout. So once we change the layout, it will impact on the people working there, and also we can't actually foresee whether the changes of this layout will actually bring more beneficial, or it's more costly or poses more risk. So if we want to try to see if our bank can support more customers. So it's also hard for us to run it in the actual system. So if it's in the simulation model, we can actually change the setting of a simulation model and try to see if with the current operation of the bank, if there's an increase of 30% of customers or up to 50% of customers, how will the bank operation react? Will the bank operation be paralyzed by too many customers? So on and so forth. So basically, what we want to say here is in this slide per se, it's risky, costly, and sometimes impossible for us to directly do the changes at the real system. So if that's the case, so how? So the safest alternative is to build a model. So build a model that imitates the actual system. And then we can ask several questions while building the model. So we can ask questions like, what would happen in the system if some of changes that you are unforeseen occur in your system? And how will you overcome or control those changes? So in short, simulation model or the model actually gives users or gives simulation modeler or subject matter expert a very safe and controlled environment where you can test different kind of strategies, policies, and see how the system in the model react. If it's positive, then you can actually implement those improvements into the real system. If it does not give a good feedback or it does not turn out, we also do not face any risk because everything is tested in a very safe condition. So this is the definition of a model. So model is a set of assumptions, approximation about how systems work. So in short, model is an imitation of the system. So it's more cheaper to study on a model instead of a real system, like what we discussed just now. If we try the changes on the real system, example, the road in your city, it will create chaos. And so it's much cheaper for us to actually build a simulation model of the road in your city, put it into a model, and try different changes, different alternatives in the model. So therefore, it's much easier, faster, cheaper, and also safer. And you can make your mistakes 1,000 times in the computer where it doesn't count. And it's safe to make mistake in this model as compared to make a mistake in the real system. Right. So far, students, do you have any questions that you want to throw out, or can we continue? All right, so if there's no question, so I'll continue. All right, so before that, so all of us here are students, and we have some researchers and some lecturers here. So if we want to do a study using simulation, so where does it sit? So we can have this a general idea based on this view. So usually we have a system under study. So system understudy are the system that we discussed just now, be it a bank, factory, what else do we share? Bank, factory, airport. So this is what we call as the system under study, and it is the real system in the real world. So then we build a model out of the system, which is an imitated model. So now we can see we are entering the simulation study arena. So once we have the model, So we will conduct several experiments using the model, and then we do some analysis, and then we have a conclusion which strategy or which improvement is the best, and then we will implement the improvement in the real system. So after we implement the improvement in the real system, and now the system under study becomes an altered system or an improved system. And as time goes by, these altered systems will be now the new system under study. So, and when the system runs for a period of time, we may need to again look at the behavior of the systems, look at the performance of the system. Does it needs to be improved further? If it needs to improve further, then again we go to the cycle of building a simulation model of the system, do experiments, so on and so forth. So if you are interested to conduct a study or a research using simulation, and you have difficulty of how to work with the process, so this is the most simplified process of how is the relationship between a simulation model in a simulation model versus the actual system under study. But of course, depending on which simulation method that we are using, they will have another different research steps. So this is roughly the general one. All right, so simulation itself, as what we discussed, lengthy discussion just now, simulation is a tool. Simulation is a research method, and simulation is a tool. So just like our examples here, we can see the hammer and the chisel, and then we can see this drill. So a tool, if we use correctly, then it's a great tool. If we use the tool not at the correct place, we can still use the tools, but it defeated the strength of the tools, right? So let's say we have this hammer and this chisel. So it's a great tool to break a wall, right? A cement wall or a concrete wall. So if you need to break walls that are harder than this brick, you may need to use probably a drilling machines, and drilling machines may be more powerful, and you might not need to use much of your energy as compared to the hammer. So these are all appropriate tools to drill a hole at the wall. So if we look at the example on the left, right, where we're trying to hammer a nail, not using a hammer, but using a spanner. So this is clearly not the right tool to drill a hole for the nail. But you may possibly drill a hole as well, but you may face the risk of hurting your fingers, or maybe you face the risk of defecting your tools. Right, same goes for simulation as well. So simulation is a tool, which it is a powerful tool to solve many different kinds of problems, but not all problems are suitable to be solved using simulation, especially if the problems can be solved using different methods, let's say mathematical methods. So if the problems can be solved using other simpler methods, usually we will opt for all the other simpler methods. Only when you would like to model and systems, and you want to make some improvement to the system, let's say you want to test different kind of strategies, policy improvement, you want to look at what if scenarios, what if you do this, what if you do that, and how will the system react. If you want to have that kind of study, then simulation is a more suitable tool. So simulation will not give you an exact answer. So if you want to find an exact answer, so you may opt for optimization method. So simulation is a method that do not give you an exact answer, but it will give you different alternative. You may try and or test different alternative and choose the best one. So simulation itself may not generate or give you directly the best situation or the best answers. You may need to still do a first or second round of analysis. All right, so let's look at this part. So like we mentioned just now, different tools are for different purposes. So there goes for simulation as well. So there are different types of simulation. So let's see how many types are there. So these are actually the evolution of different kind of methods. So the foundation of all simulation techniques actually comes from mathematical techniques. So if you can see from the earliest of time, we start with differentiation equation, which will then evolve to different kind of simulation methods. So if I can do a summary from this slide, actually currently per se there are three most commonly used simulation technique, which is the first one is system dynamic, and then second is queuing model, or what we call it as discrete event simulation. And then we have another one, which is multi-agent models, or we call it as agent-based modeling. So these are currently the three different types of simulation widely used in the industry and also in the research world as well. So what are the differences between all these trees? So the first one, system dynamic, is actually focusing on the strategic level. So if you want to simulate something related to strategies, policies in the next 5 to 10 years, so it's suitable to use system dynamic. So for example, let's say we take the perspective of sustainable innovation. So if you want to look at environmental policies, how does it impact on the climate change, and how to achieve net zero? And if we want to look at those things and its impact to, let's say, environment, investment, trades, and productivity, so those are suitable to use system dynamic simulation. Or we want to look at strategies, how to reduce emission from a certain industry, let's say from the transportation industry. What is the best way to reduce emission? Or we want to look at how to reduce carbon dioxide emission, and then how to reduce CO2 emission without affecting the current industry, and how to increase the industry competitiveness by reducing CO2 emission. So all these are higher level of decision making, which is all at the strategic level and policies level. So if we want to simulate strategies such as the one that I mentioned just now, system dynamic is the best tool for that. And if we want to look at the individual level, example, how to influence people to adopt green initiative, how to influence people to reduce the usage of single plastics, and then how can we simulate human activities at urban area environment. So when we want to model personal level, how we want to influence a person to another person, and to the extent the entire community, if we want to simulate those kind of things, it's best to use agent-based modeling. So for our class today, we will actually focus on discrete event simulation. So discrete event simulation, it's a simulation tools that has its strengths on operational level, especially on operations that have processes. So for example, I used to give these examples in class. If we want to simulate a restaurant, let's say a McDonald's, so it's a fast food restaurant, so we can see if we want to look at the operations, let's say from the moment the customer enter the restaurant, he or she will walk directly to the counter, and then at the counter, the customers will be served. And then after getting the food, then the customer will walk to the chair or tables to have their food. And then after that, they will come up from the chairs and table, whether they go to the toilets or they may leave the restaurant. So if we are trying to model processes, operations which have processes, so many small processes, so discrete event simulation is the best tools for it. So there are three types. In short, there are three famous types of simulation tools, where system dynamic focusing on the strategic and policies level, discrete event simulation focusing on the operational level, specifically if there's processes where we are interested to improve the performance of the processes, and also especially if those processes have queue. So if you want to model those kind of system, discrete event simulation is the best. And then thirdly, we have agent-based modeling, where this tool is best used to model or to simulate individual level or personal level. How can we influence the behavior of an individual, and then we extend it to a community? What kind of marketing strategy, political strategy that we can use to influence a person? Yeah, so from here we can see that different types of simulation tools are best used according to their strength. So currently in research, many of the researchers would like to cross or hybridize all these techniques. So in 10 years or 15 years back, usually a researcher will only either focus on only system dynamic, or only discrete event simulation, or only agent-based modeling. But now, due to the complexity in the industry, in the business, so one simulation technique itself might not be able to give us an understanding of the entire industry. So that's why many researchers or many practitioners opt to hybridize these techniques so that they can see more things. So they can see the strategic level as well as the operational level, and as well to the individual staff itself or individual customers. So it's now a trend to actually hybridize two or more simulation techniques. Right, so let's proceed. Okay, so this is a small impression on the three different types of simulation. So system dynamic focus on strategy, policies. So they look at the aggregated variables. So they emphasize more on the feedbacks of each variables, how one variables influence the other variables and ultimately influence the entire system. So that is system dynamic. The keyword is focusing on strategies, policy. And then we have discrete event simulation, which focusing on the operational level, specifically if the operations have processes, sequence of operations, and then they have queues in each of the processes, and then they need resources to work on the processes. So this kind of settings, it's suitable to use discrete event simulation. And then we have another one, which is even lower level, which we call it as agent-based modeling. If we want to look at individual, personal, how to influence the behavior of a person. And then for this, it's suitable to use agent-based modeling. Right, students, any questions so far? If no questions, then I'll proceed further. So, because our class today will be focusing on discrete event simulation, so let's dive deep and see what is the real definition of discrete event simulation. From the last two slides, we already understand that discrete event simulation works the best for operational level. So let's see what is the more definition of DES. So DES is a method of modeling a system. Again, yeah, simulation involve modeling a system. So DES methods of modeling a system by evaluating a series of activities at the time they occur. So imagine the example of McDonald's just now. Customers enter McDonald's, the restaurant, and then if there's a queue, he or she will join the queue, and then while queuing, and then when reaching to the counter, the customers will be served by the counter, will be taking the order, and then he or she have to wait for the order to be produced and then receive the food. Probably the customers will go to another place to collect sugar or pepper or ketchup or chili sauces. And then depending if there's a queue there, the customer will also queue. And then after getting all the necessary condiment, and then the customers will walk to the available chairs or tables to have their food. And then after that, after having their food, they might leave the restaurant or they might go to the washroom, so on and so forth. So if we can imagine this process of the customers in the McDonald's, so that is actually evaluating series of activities. So we want to see at each of those processes, does the customers have to wait for a long time? Do they have to queue? Is the queue long? So how do we improve that system? So again, DES, discrete event simulation, suitable for activity-based operational modeling. So if you want to simulate something related to strategy, what is the strategy to improve the financial situation of the restaurant? So that is suitable to use system dynamic. Okay, and then the third one, DES typically used to understand and improve the performance of a system. So basically all simulation technique, their main aim is to understand the behavior of the system. So typically for DES, because it's very much activity-based operational modeling, so its main strength is to actually look at all this series of processes, how we can actually improve these processes further. Like we mentioned just now, if there's a long queue in each of the processes, how can we improve the system further to reduce the queue, to reduce the waiting time, to reduce the total cycle time of a customer in the system? And if the processes produce waste, too much waste, how can we reduce those wastes? So on and so forth. So I actually look for a few examples of on the application of discrete event simulation in the area of sustainability innovation, which is much more related to your area. So you can see there's many research done out there. Like the first one, which look at the how to improve energy efficiency for a vehicle assembly industry. How can we help the company to be more green? How can we help the company to reduce unnecessary energy usage? So we can actually also model it using discrete event simulation. And also DES is also being used in solid waste management. How can we improve the decision making in this solid waste management? And then we also have discrete event simulation being used at a port. How to manage the traffic in a port and how to reduce the carbon footprint on the operations of the port. And we have a few more. We have utilization of these two techniques plus with DES to model a more sustainable manufacturing. And then we also see that DES can be used to simulate different kinds of requirements or specification for a more sustainable manufacturing system design. So I have more examples at the second page. So I'll give you all a few seconds to browse through these topics. If you have any questions, you can shout out loud. Okay, I have another page, another few more seconds for you guys to look through. If you need some time to look at these titles, just let me know. So all these three slides here, so I specifically choose the application of DES related to sustainability, innovation, and also environmental impact, looking at our audience. So if other than these few keywords, discrete event simulation actually is quite a popular method of simulation. So it is widely used in many kind of industries. Any industries or any systems that involve processes, like we mentioned just now, that first involve processes, and your intention actually is to improve the operations of the processes, improve the processes, and the processes involve queuing and resources. Those situations or those variables itself, it's already eligible to use discrete event simulations, or we call it as DES. And currently there are so many types of DES software out there. So one of the software that we will use afterwards, after lunch, is we call it as Arena Rockwell software. And these papers shared here are the very recent papers. So if you are looking for a research topic, either for your undergraduate studies, your masters or PhDs, you can actually visit all these papers. And if you want to look something other than sustainability and innovation, you can always Google it, and they will have lots of research done on DES. And alternatively, because our class is on DES, so I'll focus much on DES. If you are interested to look at the similar theme, sustainability environment using system dynamic, you can also look at that. Or if you want to look at the individual level, personal level, you can also Google agent-based modeling, sustainability, innovation, or environmental impact. Or you can just change the keyword into something else. You can change it into marketing, a strategy, per se. And then now it's popular with circular economy. You can actually look at circular economy using different types of simulation methods, depending on whether if you want to look at the strategic point of view, operational point of view, or from the individual or personal point of view. All right, so I guess you all have already read through or glanced through these topics. Yeah, so these are the available software. So we have three main simulation techniques here. SD is system dynamic, DES is discrete event simulation, and then we have ABM, which is agent-based modeling. So we see here there are different software here under system dynamic. We have ISE systems, we have VenSim, and then we also have PowerSim. And then for DES, we have Arena, which we will look at it in more detail in our class. And then we have Simio, we have Simul8, and then we have JumpSim. So JumpSim is one of the few open source simulation. So you can check JumpSim out. And then we have agent-based modeling. We have AnyLogic. So AnyLogic is currently the, if I can say, the only software that is capable of developing system dynamic model, DES model, and agent-based model inside one software, under one software. Whereas for the rest, it's more specific to the type of simulation. So AnyLogic is the only one that I know. Probably there are some as well which I did not came into per se. So AnyLogic is the only one currently. And then we have NetLogo. So NetLogo is also an open source platform that dedicated to agent-based modeling. So all the other software here, they also provide a student version or trial version where you can try the software without purchasing the entire full spec. So of course there are limitations if you use the trial version or the student version. All right, so we will go to the second part of introduction or to simulation. So in our previous sections, we talk about simulation. We try to understand what is simulation. So we already learned the definition of simulation. Specifically, what is the difference between model and also system? In the early stage of simulation class, we really have to have a clear understanding on what is a system and what is the model. If you do not get these two concepts right or understand it in the beginning part of our class, you might have difficulties in imagining what is the differences between a system and model. So we already covered that in our I think around 50 minutes earlier. And then we have also looked at different types of simulation. We also talk about discrete event simulation, system dynamic, and also agent-based modeling. And we also look at different types of softwares related to the respective types of simulation. And I think that's what we covered so far. So now we will go directly into the fundamental concept of simulation, specifically discrete event simulation. So these are a few concepts that we need to understand before we dive into our model building process. So now we have a system. So like just now in our earlier part, we already understand what is a system. So let's say now you already have a system. So you need to decide what you like to know about the behavior and the performance. Yeah, so you have a system. Let's say you have a bank, right? You have the bank is your system. So what do you want to see from the bank? Of course, usually we want to see how efficient is the bank operating, how efficient is your staff, how efficient is the resources, and then is the available resources enough to accommodate the incoming customers. And we also want to understand when is the peak hour of each day. Is there a certain pattern on that? And is there any breakdown of machines, or is your resources at work on time? So those are the common things or elements that we see to indicate whether the system is performing well or not. Right, so let's look at this one example here. This is a simple processing systems where we have red balls here. So you have arriving blank parts, which is the red balls, and then we have a machine here, or we call it as a server. So we see all these blank parts comes in, arrive, and then they will enter the machine, and this machine will actually serve these blank parts. So the queue here will follow first in, first out. The first parts that arrive will enter the machines, and then the second parts that arrive, if the machine is in use, the next part will queue. So if the machine has already served the parts, and then the next parts will enter the server, so on and so forth. So this is representing a small portion of manufacturing facility. So I already have explained here. So blank parts arrive at the drilling center. So imagine this is a drilling center to be processed by a single drill press, and then it leaves and it comes, so on and so forth. So this is actually a system. So what do we want to see from the system? That is the main thing that as a modeler we have to think. So a modeler not only needs to imitate the process of a system in a model, not only have to transform a system into a model, so we also have to think, what do we want to see from the model? If not, the simulation model that we develop will defeat the purpose, right? So we have to always know the objective of our simulation model. What do we want to see? So we can actually collect a lot of data from this small manufacturing facility. So usually we have data like how many numbers of parts entering the drill center, and then we also have the arrival time of each parts. What is the arrival time of part number 1, part number 2, part number 3, so on and so forth, and then also the inter-arrival time of all the parts. What is the inter-arrival time between part 1 and part 2, and then part 2 and part 3, part 3 and part 4. So the inter-arrival time actually can give us different information. It actually can show us how ready are our facilities to serve all these customers. Because if the inter-arrival time is lesser, it means that if our resources could not successfully serve the parts, there will have a long queue. And also we have service time, how long this drill or driller use to serve each of the parts. So you see here, although the parts are all similar, but the driller may use different duration to serve each of these parts. So these are all the data that we collect, and then assuming that the simulation will stop at 20 minutes, and if there are any parts at the drill press or waiting at the queue, they will not be served. Okay, so in short, these are what we call as input data, data that we input into our simulation model, input data. Okay, so now you have collected such information. So you already know what you want to model. You already have your input data, all the arrival information that we have just now, and also the service time of your resources. So now what do we need? So what we actually need is we need to decide what output performance measure that you want to collect. So once we have our model, and then once you have fit in all the input information, next we need to know what do we want to get from the model. Once we run the model, and then we have the output. So what kind of output do we want to see? So these are the typical, the basic output of most industry. So usually we want to see the total production of parts. How many parts are being served throughout a duration of time? How many tables or chairs are being produced? How many cars are being manufactured? How many cakes are being baked? And then the average waiting time of all these parts in the queue. And then the maximum waiting time. What is the longest duration that these parts have to wait in queue? So these parts can actually be used by other things like students, patients, or depending on what are we simulating. And then we have the time average number of parts in queue. How many parts are there in a queue at the time? So this actually will give us an impression if our resources is working efficiently, or the capacity of our machines. If there are too many queues queuing waiting to be served, then we might actually think of how to increase the queue time and the number of parts queuing. And then we have a maximum number of parts in queue, and then average and maximum total time in the system. How long does the parts spend in the entire system? So if we use the example of the restaurant just now, so how long do we spend in the restaurant. So that indicates to a certain degree the efficiency of our resources, our staff in that restaurant servicing the customers. So let's say the customer spends around 2 hours in the restaurant, and 1 hour of the time is spent in queue. So it clearly shows that there's something not efficient in our process. And then the last one is the utilization of machine. Do we utilize to the maximum the available resources? If yes, then we might need to think of adding another machines or finding ways to improve the efficiency of the machine if the machines are not being used fully. So these are the by default output performance measure that can be generated using Arena software. If we want something more than that, for example, if we want to look at example what is the total carbon footprint generated by the factory, or we want to look at what is the total consumption of energy, or specifically what is the consumption of energy for each of the processes, and then what are the wastes generated by each processes, and then what are the recycle rates or rework rates. So if you want to know something that is not by default, we can actually do some settings at the simulation model. And then at the end, when we run the simulation model, it will give us all this by default output, and also all the other outputs that you are interested to look at. Right. So in summary, the purpose of output performance measures is actually to tell us the current situation of the system, whether the system is working well or not working well. After gathering all this information or all these data, then only we know if we should improve the system further. If we need to improve, which part do we need to improve? So all these outputs are important. So therefore, at the beginning stage of building a simulation model, we have to really specify what are the performance measurements that we want to gather. Only by getting the correct performance measures, then only we are able to understand properly what is the current state of the system and what are the improvement that we can specifically do to improve the system. All right, so now we have input and then we have output. Input are those data that we fit into our simulation model. Example, the arrival data, the service time, the inter-arrival. So those are inputs, the one that we discussed 3 slides earlier. And then we have inputs and then we have outputs. Outputs are the service time, waiting time, queuing time, utilization of machines. So how to transform the input to output? So in the examples here, we have 3 examples here. We have the seed of a mango, and then we have the mango plant, which already have ripened mango fruits. So clearly it's the seed is the input and the fruit is the output. So our challenge here is how to transform the input to the output, right? So the process of transforming input to output is what we call it as a model logic. So if we use the example of this mango tree, the model logic will be, so first we have to clean and dry the seed, and then we have to remove the outer lining of the seed, and then clean the inner lining of the seed, and then we have to sprout the seed, and then we have to check if the seed sprout, and then we have to put some fertilizer, and then we have to check the growth of the young sprout, and then once it's healthily grown, and then we can change it into a proper place where the mango sprout will turn into a mango tree. So these are the processes. So in a simulations model, so we call it as a model logic. So model logic is the steps or the processes or the simulation model that we will build. So we will learn how to build model logic in our class after lunch. Okay, so basically in summary, what you have to clear in mind is before we build our simulation model, first you need to know the boundary of your study, because a system, as we discussed earlier, the system is a big thing, it's the real thing, which is complicated and so many uncertainty in a system. So usually we build a model to understand a system, and we cannot build a model of the entire system because the system itself is too big. So model, usually it's an imitation of a system, and it's actually a smaller version of a system. So we actually have a scope. So we have to actually understand for what purpose are we building the simulation for. Then only we have a setup of where is the boundary or where is the scope of your system. So once we have a smaller version of a system, which we now call it as a model, so you have to identify what are the inputs. We have to identify what are the inputs because we have to collect data. So usually if you are building a model of a restaurant, then you might need to go to the restaurant to collect some information, some inputs. If you are modeling a factory, you have to go to the factory to collect some inputs. If you are modeling an airport or a bank or a supermarket or even a highway or even a hospital or a universities, you have to go to the actual place and then observe the processes. So by observation, you are able to successfully transform the systems into your simulation model. And then we have to decide what data to collect. Usually, data to collect are the arrival time of all the entities. We will talk about entities in our next section. If we make it simple like a restaurant, we have to collect the arrival of customers, and then how many processes that the customers have to go through before they get their food, and how long, how many resources actually serve each of the processes, and how long each processes, and how long is the queue. So all of those things are the input. And once we have the input, we have to decide what output do we want to get after we run the simulation model. So output, the general output are the one like we discussed earlier on, the one that by default will be generated by Arena. So those are the total waiting time in the system or the cycle time, and then the queuing time, process time, machine utilization, so on and so forth. So depending on how many processes that we have in our model, so we are able to gather all those information specifically for each of the processes. So if we have something else that we want to generate from the model, output per se, so we have to command the simulation model to actually give us the report. So all of this we will learn in our next part of class. Okay, so once you have that, then only we can start to do our simulation model. And another thing about simulation model is it is very important to validate and verify your model. So because we are not the subject matter expert of the system, so let's say again the example of a restaurant. So because our role as a modeler, we are not familiar with the operation of the restaurant. So therefore, after we build our simulation model, we have to bring our simulation model and show it to the restaurant manager or restaurant management to actually verify our simulation model to see that to see that if our simulation model really imitates the actual process. So this is actually very important. If we actually did not build the simulation model according to the actual restaurant, so we might face the risk of generating a wrong output, and it will actually affect the decision making later on. So that's why validation and verification it's one of the process that all modeler have to go through. So after validating your model, then we can try different types of strategy to improve our simulation model. All right. So we are actually towards the end of our first part of class. So what we have actually discussed so far is the definition of simulation. And then we talk about systems and also models. What is the differences between systems and models? And then we look at different examples of systems. And then we also talk about the types of simulation. We have discrete event simulation. We have system dynamic, which focus on the strategic and policies level. And then we have agent-based modeling, which its strength is on modeling the individual and personal level. And then we choose one of them, which is discrete event simulation, to be our main topic of our class. So we have a lot of discussion just now on discrete event simulation. And then I also show some of the application of DES specifically in environmental issues, sustainability, innovation issues. And then we jump straight to the second part of the morning class, which is the input and also the output. So what needs to be first specified when we want to build a simulation model, which is the input, where we have to gather all the information and feed into our simulation model. And then we have to decide, after we run the simulation model, what are the performance measurement or output that we want to see. So once we have all these things in place, and of course you need to know the boundary of your simulation, of your model, how to what extent of complexity that you want to imitate the actual operation. So once you have that in place, then we are ready to actually simulate your system. Right, so before we go to our part 2, which will happen after lunch, so I hope you can download the software first. So in the afternoon, we have a little bit of hands-on. So while having your lunch, please download this software, put it into your laptop, and then you can also try and drag and drop some variables in the software, and then you try to play around the software. Right. So any questions so far? Yeah. Any questions so far? If no questions, we might have a break, a lunch break, and then we will be back at 1 o'clock Thailand time and 2 o'clock Malaysia time. Or if you are shy to unmute your mic to ask questions, you can always type at the chat box and I'll read your questions. If not, then we'll go for a break. So we'll be back at 1 p.m. Thailand time and 2 p.m. Malaysian time. All right. Thank you. See you later.
Good afternoon, Professor.
Sustainable Industrial Management using Simulation class. So I will share my slides. So I hope all of you have taken the time to download the software. So we will have some hands-on session afterwards. All right, so let's pick up from where we stopped before lunch. So before lunch, we talk about the definition of simulation, what is simulation, and then the two important terms in simulation, which is the system and also model. So system is the actual process, and model is actually an imitation of a system. So it's hard for us to investigate or make improvement directly to the system because it will disrupt the operation of the system. So that is why we build an imitation or a model or a small part of a system using simulation. So in this model, we can do any improvement in a very close and a safe space. So it's even cheaper, less risky to conduct experiment inside a simulation model. So in the simulation model, we can do as many mistakes as we want, as many trials as we want, and it will not impact on the actual operation as compared to if we do all this improvement to a real systems. So system, as we discussed earlier on, we look at different types of systems like the bank system, and then we look at a manufacturing system, a restaurant system, McDonald's, which we mentioned many times before this, and then we also explore healthcare systems and supermarket system, which all we discuss in the morning. And then after that, we also talk about different types of simulation. Simulation is the evolution from a mathematical algorithm, and of course, with the advancement of technology, these days we have kind of user-friendly simulation software, where in the older days we have to do coding of simulation model. So the modeler needs to have to a certain degree of programming background. But these days we have a lot of user-friendly simulation where you do not need to have programming background. You can just drag and drop all the modules into a platform, and then we can just create the simulation model. So we have discussed on 3 different types of simulation technique, where the first one is system dynamic, which focus on the policies strategic level. And then we have discrete event simulation, which is the main focus of our study. Discrete event simulation focusing on the operational level, on processes, especially if we want to do improvement on a process. And then we have agent-based modeling, where agent-based modeling, its strength lies on modeling or simulating the behavior of individual or at the personal person level. So it's the lowest level compared to the strategic view of using system dynamic. So our focus is on discrete event simulation again, and we also discuss on several examples of discrete event simulation application especially focusing on sustainable innovation and also environmental impact. And of course, there are many more examples on the implementation of discrete event simulation, which you can check online or Google Scholar or any of the journals that your library subscribe to. And also, we also jump into the concept of discrete event simulation, where we talk about input, all the information or data that we need to gather to insert into our simulation model. And then we have performance measurement, all the outputs that we would like to gather after we run our simulation model. And performance measurement, the common one will be all the waiting time, service time, queue time, cycle time, resources utilizations. And also, we discuss a little bit on how to convert input to output. In the middle, we have something called model logic. So we need to have the model logic, or we need to develop model logic first before we can actually run our simulation model and get the output that we want. So if we would like to command the simulation model to generate output which is not the conventional one, which I mentioned just now, all the total time, waiting time, service time. If we want something else, we can also demand the simulation model to give us the result. So in order for us to demand such results, we can have some formulation in that simulation model, which we will look at it later. So all these are what we discussed earlier in our first part. So moving to the second part, we will actually dive into using ARENA simulation model. So like we mentioned earlier, there are many different types of software tailoring to each different types of simulation. So as of discrete event simulation, there are many different types of software available. So today we will use one of those many software, which is ARENA. And one thing about all the simulation software, as long as you are familiar with one, you will be able to use the rest. Because the settings and the interface of all those software is a little bit similar. All right, so with that, we will proceed. Also, before that, I hope all of you have already downloaded the software. And let's go to part 2. So part 2, we will be focusing on exploring ARENA simulation software. If you want to know more about ARENA, you can always Google Rockwell ARENA. So Rockwell is the company that produce or that manufacture ARENA. Okay. So before we move into the hands-on part, so all these 4 terms we already covered this morning, so I will not go to these 4 terms again. So we will talk about another 4 terms or 4 jargons which heavily used in discrete event simulation. So if you are using system dynamic or agent-based modeling, they have another set of different terms. So these 4 terms are the most frequent used terms in discrete event simulation. So the first one, we have entity. So entity are actually players or things that move around. The status of these players will change, and then these players will also affect and are affected by the state of the systems. And these players will also impact on the output performance measurements. So usually when we want to start to create our simulation model, we have to first create the entity. So entity in short is things that we create that will move around our model or move around the system. So an example, if we use our restaurant, so entities will most likely to be the customers. So customers will be created, And then the customer, once created, will enter the restaurant, will walk around the restaurant, will move to the counter, queue at the counter, waiting for the resources to serve the customers. After getting their food, they will walk to their tables and chairs to have their food, and then after eating their food, they will walk around anywhere that they want in the restaurant, and then after that they will leave the system. So that is what we call as entities. So in the case of a restaurant, if you want to model the operation or the efficiency of a restaurant, then customers might be the entity of the restaurant. Another example is if we are trying to model a hospital. So the most probably the entity will be the patients. So patients will enter the hospital, and then they will go to the whichever department that they would like to meet their doctor, and then take a number, and then wait for the next process. Like maybe they have to go and take their x-ray, go take their urine, or go take their blood, or and all the other process, and then finally got to meet the doctors. And then after that they have to go to the pharmacy to get their medicine, and then after that they will leave the hospital. So the movement of these entities are the things that will affect the output performance measure, because all these entities will move around the system and will be served by resources in the processes. Right. So another example, if it's in the university, so most probably entities will be students, or can be lecturers, or can be administration staff in the universities. So before we can build our model, before we start to build our model, first thing first, we need to decide what will be our entity. So our entities actually largely depends on the objective of your study. What do you want to model, and to whose perspective? Because sometimes in the university, we have lecturers, students, administration staff. So depending on the objective of your studies, these trees can be the entities, or maybe only lecturers, not students, or sometimes only students, not administration staff, depending on which processes you want to see. And second is the attributes. So attributes are the characteristics that we give to the entity. So example, we would like to only model, or let's say we would like to see the students, where we can attribute it as male and female, or via age, or via if it's senior citizens, we want to give some priority to the senior citizen in terms of the service, and then in terms of the time of arrival for the entity. So attributes are all the characteristics that we give the entity, so that we can differentiate one entity with the other entities. And then number 7, we have resources. So resources, as we all know, resources are things that we use to serve a process. So resources are things that entities compete for, because resources are pretty limited, and entities, we have many entities. So all the entities that come into the model or the system will be competing to get the resources. So resources can be people, can be equipment, can be space. So again, our restaurant examples, the resources may be the staff working at the counter, can be the staff at the kitchen, can be all the cooking utensils in the kitchen, because all those equipments may have impact on the customers or entity waiting time. And then space can also be resources. Example, if we want to model a warehouse, so the availability of space to store all the goods, whether it's finished goods or raw materials, those are space. And then we have queue. So queue are the place where entities have to wait when the resources is not available. So whenever an entity move towards a process, if the process the resources is being used by another entity, so the entity have to queue waiting for the entity before them to be served completely by the resources and to be released from that process. Then only the entity can be processed by the designated process, so on and so forth. All right, so these four things are the most important terms that we use in a discrete event simulation. But of course, there are many other terms that you will get to know along the way while exploring discrete event simulation. But for a start, we have to understand these four things. I think number 7 and number 8, resources and queue, easy to understand because we usually use that in our daily life as well. The one that usually challenging for students is entities and how to differentiate entities with resources. So you have to differentiate. Entities are the things that move, the things that we create in our simulation model and will move around the simulation, being served by the processes and also its resources, and then leave the system. So that is entity. Resources are things that tie to a process and will serve the entity. So I hope you get a rough idea on the differences between entity and resources. Okay, so now let's look at Arena. So afterwards, I will demo it in the software, but first let's use these slides as a guide. So Arena, once you download and you launch it, it will look something like that. So depending on which version that you downloaded, so if you use the link that I shared, you will get something like this. So this is actually the older version of Arena. Arena currently also have a newer version. If you go to Arena website, so the current version will have will be more colorful than this. So because I am a frequent user of the previous version, so I just continue using the previous version. On the functionality of both versions, it's equally good. Okay, so once you open the Arena software, you will see something like that with 3 windows. And then we have the empty platform on the top. It's where we use to develop or to drag and drop our modules to develop our simulation model. And then Arena also follows the Windows application. So if you are very familiar with Words, PowerPoint, Excel, you will be able to navigate through Arena because Arena also have the same setups. We have file, edit, view, tools, assign, and it's very much user-friendly to use. And then we have also all the draw, words, text, copy and paste and save, all are according to what we are familiar with. All right, so let's go to the next one. Like I mentioned just now, there are 3 windows in Arena. The first one on top where we will actually build our simulation model is called flowchart view. And then the window below flowchart view is what we call as spreadsheet view. And then the flowchart view is where we drag and drop all the modules that is available at the project bar, if you can see. And then once we drag and drop all the modules to the flowchart view, and then the spreadsheet view will also appear if we insert any data. And then if you want to close either the flowchart view or the spreadsheet view, you can always push on this split screen. The split screen button is next to the amplifying button in Arena. Okay, and also if you look at your project bar, there are also many different types of modules available depending on your need and depending on what kind of process that you are trying to build. And in project bar, there are also 2 types of modules. The first, we call it as flowchart modules. like what we see on the slide. And also we have another modules called data modules, which in the form of spreadsheet. So both of them are actually input data and also modules to imitate your simulation model. All right, so now I will go to the arena model. You can see. So like what I mentioned just now, there are 3 windows here. This is the flowchart view, and this is the spreadsheet view. So at the project bar, we can see a lot of different modules that you can use. So for a start, we will use all the modules at the basic process. So from this project bar, we also have 2 types of modules. So this is the one that we mentioned just now. What is that? Flowchart modules and also data modules. This is flowchart modules and this is data modules. So usually when we want to create our simulation model, the first module that we will use is the create module. So how should we drop our create to this canvas? We just click on the create, just click. So you see when we click on create, automatically the spreadsheet view will also have this row created. So you just click and then you drag and then you drop at your canvas. So now we have one create. So when you click here and then you see at the spreadsheet view, we also have all the information here. So you can double click, you can name it, any name. You can name it as students arrival. So when we name the process as students arrival, so we immediately know that the entity for our model is student. So the entity type here, you can type it as students. And then we have the time between arrival. So this information here, you need to do some data collection, like the one we discussed in the morning. We have to have some data on the arrival of students, and then student 1, student 2, student 3, and then we need to have the inter-arrival of students, the time between arrival for students. We also need to have that. So we also support, Arena also support different kind of distribution according to your needs, and then we can add whatever value according to what you want. And the units as well, we have from second, minutes, hours, or even days. And also we can also set how many entities that will arrive at the same time. Meaning that in one time, only one entity come at the time, or 10 entity comes at the time, or 20 entities come at the time. So you will be able to do that setting. And also we have maximum arrival if we are modeling a restaurant or let's say a hospital. So we do not set that one day we will only serve 10 customers. So we will take in as many entities as possible, as many students as possible, as many customers as possible. So therefore the maximum arrival will be infinite. So if like if we are modeling some manufacturing process where they have a certain cut off for their resources, they might only able to serve, let's say, 50 parts in a day. Then the maximum arrival for your model will be just 50. So in this case, we can just leave it as it is. So this is the place where you create your entity. So your entity is a student and we created a student. So if you notice, whatever that you type in this box is also recorded in the spreadsheet view. So in short, you can actually double click and type all the information here, or you can click on this, and when this sheet appear, you can actually type all the information here as well. So the purpose of this spreadsheet view is for us to visualize all similar modules at once. So let's see. So after the students arrive, so where do they go? So let's say this is the student registration process. So after the students arrive, and then the next process, they will go to register do some registration. So this is the second process. And then after that, maybe after registration, they will go to take their goodie bags, and then they have another process. And then after that, probably, and then they will enter their, let's say, classroom, and then another process, so on and so forth. And then at the end, after the students completed the event, and then they will be disposed. So if we have create, we also need to have dispose. So this is a create module, and then these boxes are all process module, which we will use this process to define all the processes that the entity needs to go through before being disposed. So dispose is after the students have already gone through all the process and being served by the resources, and finally they are leaving. So we also have to join all these processes using this button here. We can connect it, and so on and so forth. So if you see, if we click on the create, the spreadsheet view will show just one row. So let's say we have 3 different processes. If you click on one process, it will appear all three processes that we created. So you can use this to actually change its name or put all the relevant information. If you don't want to do it here, you can just double click, put on it separately. Right, so let's say this is the registration process, student registration. So we will put cease delay release. So cease delay release is the process or the action where when the entity arrive at this process, it will actually cease the resources, and then the entire process will be delayed, so that the resources can serve the entity. Once the resources completed the serving the entity, and then the entity will release the resources, and then will leave this process, and then the next entity in queue will enter the process. So when we have it like this, and then we can put the resources, assign the resources. How many resources are we assigning? What is the name of the resources are we assigning? So you can name your resources as counter 1 or staff 1. And then how many entities that the staff will cease? Can the staff just serve one students at a time? So you put 1. If the staff can serve 2 students at a time, then you put 2. Then you click OK. And then you need to also include how long will this process take place. The students registration, how long students spend in this student registration process. Probably it's only 5 to 6 minutes. And all this information, you need to collect the data. So you put OK. And then once you type all the information in it, all the information will also appear here. And then you can go to the next process, and then being disposed. If we do not dispose our entities, the entities will be lingering around your system, and the system will finally explode. The model will finally explode because you created many entities, but none of the entities leave the system or leave the model. So always remember, once you create, we have to release or dispose the entities. All right. Any questions so far, guys? All right. If no, I'll proceed. So I'll show you one example. Let's see one example. Okay, so this is an example of simple processing system. Maybe it's easier for you to understand. And also Arena also gives us the flexibility to plot a graph depending on what kind of graph do you want to see. So in this case, it's queue length and also number of busy. Number of busy meaning number of resources. Number of resources being, not number of resources, number of entities served by the resources. Right? So same, all simulation model using Arena, we need to start with and create, because in this create module is where we create our entity. So as this is a model of a simple processing system, so therefore our entity most likely will be parts. Actually the queue is in the clue is at this create module, because once we see parts arrive to the system, we can roughly gauge that parts will be the entity. So if we double click here, so we name this process as part arrives to the system, and then obviously entity type is part, and then the time between arrival of the parts, meaning from part 1 to part 2, in between, after part 1 have arrived, and in between the time arrival before part 2 is arrived, and then the in between of the arrival between 2 and 3, 3 and 4, and so on and so forth, roughly the modeler used random exponential 5 minutes. So exponential 5 minutes is the estimated duration between arrival of each entity. And also each time one entity arrive at a time, and they are accepting as many entities as possible. So that's why they put it as infinite. And then once the parts are arrived, and then they move to a drilling center where the parts will be drilled. So we double click. This process is called a drilling center, and then the action is also cease, delay, release. So I already included also in my notes the definition of all: delay, cease, release, and delay, release. So once you all get the slide, you are able to read the definition again. So again, as I mentioned just now, cease, delay, release is where the parts cease the driller. So the drill press will be the resources in this drilling center. So the parts arrive at this process, cease the drill press, and then the entire process will be delayed while waiting for the drill press to serve these parts. Once the serving completed, then this part will release the drill press and then move to the next process. And the next entity or the next part will be able to enter this drilling center. If the resources or the drill press is still serving the parts, the incoming parts will have to queue. So that's where the queue will build up in this line. So if we select cease, delay, release, automatically this fine line will appear on top of this process. So this is what we call as the queue line. So when we run our simulation later, all the queues will be built on top of this line. Right, continuing, after we click on cease, delay, release, automatically this resources box will appear, and then we will create add whatever resources that we think needed to support this drilling center. So we have drill press or driller, if you want to call, as our resources. So how many entities that this drill press can serve at one time? So it's 1. If you think your drill press can serve 2 entities at a time, then you put 2. And if you think this process needs to have 2 drill process, then you can just add another one, and then you have another one. Okay. So, and then the delay type. How long is this process? How long does the drill press use to serve the entity? So that is that process. We have to key in the information here. So how do we get all this information? Is depending on your data collection process. So when we want to create a module of a certain system, of course, we have to visit the place, visit the factory, visit the hospital, visit the bank, visit the restaurant, and then we have to get information or get data on the first arrival of the entities, and also for each of the processes, how many resources are there used to serve each process, and how long is the duration of the process. So all these are information that we need to collect. In short, these are what we call as input data. If you still remember what we discussed earlier in the morning, we talked about input data, output which is the performance measurement, and we also talk about how to transform input to output. We need something in the middle called model logic. So this is what we are doing now. We are actually building the model logic. So with this model logic, we are able to insert all the input data inside our simulation model, and then we run it later, and then the simulation will able to produce output that we want. So using that output, we will see whether this system, this processing system, is performing well or not well, or what needs to be improved, and then we will test different types of strategy to improve things that we think is lacking of. Right. So after completing this drill center, so this is a very simple processing system. They only have one process. So after the parts arrive and enters or being served at the drilling center, and then the parts will leave the system. So this is what we call as a dispose module. If you can see here, that this is dispose. And we just name it, and then let it leave. So once you have created your simulation model, we can actually run it. Let's run our simulation model. There you see our parts are arriving, entering the drilling center, and then you see there's a queue. There's a queue forming here. Okay, let's run it again. Parts coming in the drilling center, and then the parts are queuing after being served by the driller, and then it will leave the system. And then you see here, there's also the graph here showing the queue length. At certain time or in a day, the queue is high. There are 3 parts queuing. And then this shows the number of busy of these resources, meaning that these resources is being used throughout the duration, throughout the time of simulation, except for certain minutes before the simulation ends, where the driller or the drill press is not servicing any of the parts. All right, so after you run your simulation model, you will be popped up something like this. You will see a pop-up something like this. The simulation has run to completion. Would you like to see the results? So if you click yes, then the result will pop up. It will take some time before the result pop up, depending on your laptop. If your laptop is a bit heavy, then like mine, it will take some time. So the result is out. So you can see how many number out. It means that how many parts have being served by the entire system, successfully served. So we see there are 5 parts successfully being served by the drilling center. And then we also have the time for each entity. So what is the waiting time? And then what is the transfer time? Because this simulation is too short, so much of the information are not being able to capture. So if we are building a little bit more complicated model, you'll be able to see all the other information. So we also have some basic information, like how many parts comes in, how many parts goes out. So comes in, we have 7 parts coming in and 5 parts going out. So we have around 2 more parts in process, work in process. And then if you go to the next one, we have for all the processes, we also have the waiting time, total time. So because in this example, we only have drilling center. If you have more processes, then all the processes will appear here. So you're able to see the waiting time for each processes and the total time for each of the processes. Then we have queue, the waiting time, and then the resources utilization, whether it's busy or it's not, or whether it's idle or it's not. Yeah, so these are all the by default results or by default output. So if in cases where you want something more than the one being given, you can always go to statistics module. You can go to statistics modules, and then we can add all the formulation that we want if we want something others than waiting time, queuing time, total time. Any performance measurement or any outputs is possible to be generated using Arena as long as you know the formula and how to tie the formula with the module, and then you name it in the statistics module. Then you'll be able to get it at the result once the simulation stops. All right. Any questions so far? Let's go back to our slide and see where are we. If you have any questions, do just let me know, or you can type it at the chat box and then I'll read it. All right, so we're done on this. Let's see if I miss out anything. This one done. Oh yeah, that's one thing that I miss out. All right, so we can actually change the entity picture. Remember when we run just now, the entity is a blue ball. So we can actually change the picture according to what we like. So we can just go to basic process, go to entity, and then you see here, initial picture dot blue ball. So when we set this blue ball, and then the blue balls will come out. So if we set to other things, let's say we put picture dot boat, and then we run it, I guess a boat might come out. Yes, a boat might come out. And if you do not like the default picture given by Arena, you can also draw your own picture in the picture library and then assign the picture as your entity picture. Is also possible. Right, let's go back to the slides. I think we're pretty much done on this. On the graph, it's basically self-explanatory. You just click the graph into the canvas, and then you just decide what you want to put for the x-axis and also the y-axis. And then depending on what do you want to see from both axes. So you just define it that way. Okay, I think we're done on this on Q. Q will only appear if you use cease delay release. If you do not use cease delay release in the process, your Q will not appear. Okay, and then dispose. And then we have the setup. How long we want to run our simulation model. We can go to run setup, and then you can put a lot of information here, like your project parameter. You want to name your project, you have your name written here, and then a short description on your project, and then you also can decide what kind of output you want to see when the simulation stops. And then usually we use a lot of information in the replication parameter tag. So here we decide how many replication do we want to replicate the simulation model. So do we want to run the simulation model for 10 times, 20 times, 30 times, 40 times? So actually the more replication we run, the more accurate the average we will get. So apart from that, we also can put information like what is the replication length, how long we want to run our simulation. So number of replication is how many times do we want to run the simulation. Replication length is how long do we want to run the simulation. But it's for 6 hours, 8 hours, 20 hours, 24 hours, and hours per day represents how long is the operation of your system. Whether they only operate 8 hours, 5 hours. So all those things need some input data. So remember to collect your information, not only on the number of customer arrive or the time of their arrival, the processes, resources of how many resources in each processes, how long is each processes, and also you need to know the duration of the operation. And you can also set the time you need to be your preference, days, hours, minutes, seconds. And then we are set to run our simulation. So this software actually comes in a blank canvas. So it's depending on your creativity to build the simulation model. And there is no right or wrong in building a simulation model because it's largely depending on the modeler creativity. So probably you and your friend visit the same factory and you both might have a different simulation model depending on your own understanding and also creativity. So that is why validation and verification is very important. So once you completed your simulation model, you need to bring this simulation model and show it to the subject matter expert. So if you are building a restaurant model, you need to visit the restaurant subject matter expert. If you are building a simulation model on a factory, you need to talk to the factory subject matter expert. It can be the operation manager, operation director. And then you need to explain part by part of your simulation model, the processes, and see whether you successfully capture the model as it is happening day to day. When it is accurate, only all the results generated by your simulation model can be used for preparing the what-if analysis. So imagine if you understand the system wrongly and then you build a not so accurate simulation model, and then it generates result which we know already not accurate since the model is not accurate, and then you might fall into the mistakes of proposing not so accurate strategies or policies. So that is the danger of simulation. So simulation models, we need to do validation and verification at least 2 times. The first time we will do it after we complete the model. We will show it to the subject matter expert and show is it correct. After the parts arrive, it will go to drilling center. After drilling center, it will go to painting center. After painting center, it will go to whatever center. So does it really mimic the actual process? So if the simulation model, the processes is validated, then you can start to run it. And then once you get the output, we need to also compare it with the actual data in the factory. And once those output between the two is similar and statistically acceptable, so you have to use some statistical tools to test it. Once it's acceptable, then you can do your what-if analysis. You can do your improvement. All the strategies for improvement, you can actually test using your simulation model. So then when the results generated from all the what-if analysis, that will be more reliable since you already undergo 2 process of validation. Right, let's move. Okay, so we will go to another one, another more complicated simulation model. So before we go to this example, any questions from the students? No question, yeah, so I'll continue. Right, so after looking at two examples, the one examples that I gave on the students program process, and then we have the second one on the simple drilling process, and then now we are looking at a little bit more complicated but still at the basic level of simulation. So we will look at an electronic assembly test system. So before we build a simulation model, we have to understand the process, the actual process that happened in the system. So we actually have to write something, we call it as system description or system definition. So we will look at what is actually system definition and system description. Okay, so let's look at this. So this is electronic assembly and test system. So it is the final operation. It is the final operation of the production of two different seal electronic units. We call it as part A and also part B. So basically, this is towards the end of the electronic production process. So once the parts go through this process, it will be shipped to the customer. So we only model part of the entire system. So let's understand this process. So arriving parts, part A and part B, when they arrive, they are cast metal case, empty metal case that will be used to insert electronic parts. Right, so when they arrive, they are an empty case, and then when part A arrive, they will go to part A preparation. Part B arrive, they will go to part B preparation, and then after that, both parts, either part A or part B, will go to the sealer. So in this sealer process, the electronic parts will be inserted into this metal case, and then after that, 91% of these parts will be shipped, and 9% will have to go through rework, meaning that there's some faulty or default on the casing. And after rework, 20% will be scrapped because it cannot be improved, and 80% of those rework parts will be salvaged, meaning are able to repair and will be shipped to customers. So this is actually the final stage of the electronic parts process before being shipped or sell to customers. So what we explained just now, like all this, the journey of the parts, the journey of the entities from the moment they are created to the moment they are disposed, is what we call as system description or system definition. So as a reminder, if you want to build your simulation model, you need to know as detailed as this. From the moment the entity are created, where will it go? What is the first process that it will go? And in the process, how long will it take? And then what are the resources that will serve those parts? After completing that process, what will be the next process? Similarly, what are the resources in that process and how long is those processes? until to the moment where all these parts are being disposed. So we need to have that information clearly. If not, you will not be able to build the simulation model as near or as close as the actual system. Okay, so these are only the rough explanation. So let's go to the more detailed explanation. So part A arrives. So imagine here, part A, when it arrives, it is an empty metal case. So the inter-arrival of part A is exponential 5 minutes. Remember, how do we get this information? This information is where you have to collect the data from the company, or you have to go to the factory and to use a stopwatch to observe yourself and to count how many parts arrive, and then you have to do some statistical distribution, and then you will get exponential or whatever distribution that near to your data collection or your data, the collected data. And then from arrival point, so once arrived at the inter-arrival of exponential 5, it will goes to the part A preparation. So part A preparation is a process where the case are machined and then being cleaned. So this process will take around triangular 148 minutes. Again, triangular 148 minutes is an input data where you need to collect from the factory how long this process takes place. It is actually when we collect the data, it's all in numbers. So because it's all in numbers, it's hard for you to insert all the numbers into Arena. So therefore, you need to transform those numbers into the nearest statistical distribution. So Arena also have that function, but we will not be covering it in class. So if you explore further later, Arena has a function which we call it as Arena Input Analyzer, where you can feed Arena Input Analyzer with all the data, and then they will generate what is the nearest statistical distribution based on your data. So in this case, we get the nearest one, which we call it as triangular 148 minutes. So after completing the process at part A preparation, part A will goes to sealer. So sealer is the process where the empty casing will be inserted with electronic components, and then the cases are sealed and also tested. And this process will take around triangular 134 minutes. Again, remember all this value, data collection. And in the sealer, once they are tested, 91% of the parts, it's okay to go and will be shipped to customers. And 90% of those cases will have default, and then they will be sent to another rework process. And this rework process is a reprocess and testing process, which it will take around exponential 45 minutes. And after this rework, 80% will pass and will be shipped to the customer, and 20% cannot be saved. So it will be scrapped or it will be thrown away, depending on how green is this factory. If this factory is green enough, those scrap materials will be recycled and used again. So that is out of the scope of our discussion. So anyway, so this is the journey of part A. And remember, we have two different entities in our example. We have part A as entity 1, part B as entity 2. So let's look at part B. So part B is a little bit different from part A. So part B arrives in a batches of 4. So meaning at one time it comes in 4. So part A in one time it comes one by one. Part B comes in a batches of 4, and it follows exponential 30 minutes as the inter-arrival. So once arrived, it goes into part B preparation. So part B once arrived, it's 4. It arrives in a batches of 4. once entering the system, it will be broken down into 4 individual parts. And then process immediately to part B, preparation area, the same. The cases will be machined. The empty cases will be machined, will be clean. And then this entire process is triangular 3, 5, 10 minutes. So you see here, although the journey is the same, part A and part B is the same, but the processing time is not the same. Part A processing time is triangular 1 for 8 minutes, and part B preparation is triangular 3, 5, 10 minutes. So you have to remember on that. And then after being processed, it will go to sealer. Again, sealer have a different time for part A and also part B. And also after sealer, 91% will be shipped. The rest will need to be reworked. And after rework, around 80% will be shipped and the rest will be scrapped. Right, so this is basically the journey of part B. So in short, part A and part B follows the same route, but their duration span in each process is not the same. So once you have a detailed journey like this and a detailed input data, then you'll be able to build your simulation model. But before that, we also need to know what are the output. Remember just now we mentioned we need to have input to insert in our model. We also need to know what is the output that we want to gather when we run the simulation. So let's see. So this is the run condition and the output stated for this model. So we will run the model with an empty and idle condition. So we will run for 32 hours, 4 consecutive 8 hours shift. And you see number 2, collect statistics for each work area on. So this is the output that we want. We want to know the resources utilization for all the processes. We want to know how many parts are queuing in all the processes and how long does all the parts spend in the queue. And then for each exit point, ship, salvage, and scrap, we want to collect the total time in system, meaning that from the moment the parts arrive, right until they are shipped, how long do they spend in the system? Or from the moment the parts arrive, right until they are being scrapped, how long they spend in the system? And lastly, from the moment the parts are created, either part A or part B are created, until they are being salvaged and shipped, how long do they spend in the system? So all this information actually will give us an impression, the performance of the system, whether it's performing efficiently, effectively or not. So once we collect this information, the output, and then we will analyze the output and then decide how to improve the model. So that one is the second stage of a simulation model where we will do what if analysis. We will try different types of intervention to improve the current operation. Before we can do the what if analysis or deciding on what improvement that we should do, first of all, we need to know or understand the current state of the system, which we are doing right now. Okay. Any questions so far? So if no, we will proceed. So just now we already talked about the system description of our electronic parts process. So like I mentioned just now, before we start to build our simulation model, system definition or system description is very important. We need to know the journey of the entities, how many types of entities that we need to create, how many processes are there, how long are each processes, how many resources are there for each of the processes, and how many dispose process do they have. Like in our example, we have 3 different dispose process. So those are the definition or the journey of the entity along with the processes. So now once we understand those things, we need to find out ways to transform those information into a simulation model. So what you see in the screen now is what we call as model logic. So if you remember the mango seed, mango tree, and mango fruit, how can we transform mango seed to mango fruit? That process is model logic. So what you see on your screen now is called model logic. So we have to actually decide how or what modules to use in order to capture as closely as possible as the system description. So roughly we know that we need to have two create because we have two different entities. We have part A and also part B. So we have create 1, create 2. And then we have assign module to assign certain things that we will discuss later. We will show you the real model later. And then we have process. So after create, it will go to prep A process. So this is roughly part A preparation process. And then this is roughly part B preparation process. And then after that, they will merge and go to a process called sealer. Yeah, exactly the same like the system description. After sealer, it will go to a decide module where a certain percentage will be shipped and a certain percentage will need to go to rework, which is process 4. And after completing the rework process, a certain percentage will be scrapped and a certain percentage will be salvaged and shipped to customers. So roughly, this will be the tentative or initial model logic for our example. And our next challenge will be how to insert all the information that we collected. For example, the inter-arrival time, processing time, how many resources, how to include all those information inside our simulation model. Okay, so let's look at our simulation model. Okay, so once you have successfully transformed, I'll make it bigger. So if you don't want to have two compartments, you can just click this. If you click back, and then it will appear again. If you don't want this, you can just click this, and then you have a bigger view. So this is the model logic, initial model logic that we created for our system description. So now our task is how to insert the information. So part A is easy. This one we already discussed twice previously. So we just name it as part A arrive, and then entity type is part A, and then we insert all the given information here, inter-arrival, exponential 5 minutes. And part B is a bit different because we know part B arrives in a batches of 4. So we need to put entities per arrival 4. Maximum arrival is not stated in the system description that this process can only serve, let's say, 50 part A and 100 part B. So those information are not given. So we assume that they do not have maximum arrival. So we use the infinite, by default infinite. And then we have another module called assign here. So let's see what is the function of this assign module. So the function of this assign module is to assign part A sealer time and also arrival time. If you still remember in our model, sealer have separate, sealer is only one process, but the processing time for part A and part B is different. So you see here, part A have different processing time, part B have different processing time. So when we build our simulation model, we need to insert these two differences in our model. So that's why we use assign module, where first we call it as an attribute. So what is the attribute name? It's called sealer name. So for part A, the sealer process is as given when you collect your data, triangular 1, 3, 4. And then we also want to timestamp the arrival of part A because we need that for our output, because you want to know for each exit point, collect total time in the system. So if we want to know the duration of the parts from the moment they arrive until they ship, or until they are salvaged, or until they are scrapped, the moment the entity is created, we need to put a timestamp, meaning that we need to identify what time they arrive, and then we will timestamp it again at before they leave the system, what time did they leave. So if we have what time they arrive and what time did they leave, then we have the entire duration, how long they spend in the system. Right, so this is the purpose of that. So we have attributes name, arrive time, and then the value is T now. So T now is a formula used in Arena. So T is time, now is now. So the time now. So give the timestamp now for this newly created parts. So this is the function of assign module. And also part B follows the same. This assign module is to assign the sealer time for part A, and also the arrival time for part B, no, part A, both for part B. So again, attribute, same attribute name, which is sealer time, and then the sealer processing time for part B, and then this is to timestamp part B arrival time. Okay. Then after that, part A go to part A preparation process. So you just name your process, change into sys delay release, and then put the resources, name the resources, and then key in the duration span to process part A. Similar, do the same thing for part B. Everything's the same. All the input information that you gathered, you have to put it in here. And then after that, it will goes to a sealer process. So sealer process, remember for sealer, we have two different processing time for part A and also part B. So again, you name your sealer process, choose sys delay release, you have one resources, which is the sealer, and then the expression, we will use expression. See, we use sealer time. So when we type the expression sealer time here, so it will automatically capture the sealer time of part A, which we assign in the assign module for part A, and also it will capture the sealer time for part B, which we defined in part B earlier. So what you type here needs to be as specific as what we created. So if when we created in the assign module, we use sealer time S small capital letter and T small capital letter, and here we use S capital letter and T capital letter, it will not capture. So you need to type what you created in the assign module for both part A and part B. All three needs to be the same. And then you click OK. And then we go to the decide module where we know certain percentage will be shipped and another certain percentage will go to rework. So you just insert the information according to the given data. So for decide module, we can choose several ways. So if you have more than 2 ways, then you can use n way by chance. So you can use 3 ways, 4 ways, 5 ways, 6 ways, depending on your system. If you only have dividing into 2, like our example, so you just use 2 way. So if you want to use by percentage, you can use 2 way by chance or n way by chance. If you want it to be split not according to percentage, according to some formulas that you want to create yourself, or by any condition. You can just use by condition, and then you state the expression in the box given. Right, and next, after entering this fail sealer inspection, again, part of it will be shipped, and then another part of it will go to the rework process here. So in the rework process, you just enter this again, the same process. Do the name, write the name, choose this delay release, and then put in the duration span to complete this rework process, and then you click OK. And then remember, after rework, there is another inspection, and how many percent of a certain percentage of rework will be salvaged and will be shipped to customers, and some of it will not be able to be repaired and it will be scrapped. And before we dispose our entities, we have another modules here which we call it as record modules. So the function of this record modules is to record something depending on what we want to record. We can record the time, we can record the total number of parts, and many more depending on what you want. So in these examples, we are recording the time of the parts leaving the system, because as specified in our system description or definition, we want to collect the cycle time of the parts, right? For part A, regardless part A or part B, we want to know from the moment part A and part B are being created or arrive, how long will it spend from the moment they arrive till the moment they are being scrapped, salvaged, or being shipped. So at the beginning in the assign module, we already timestamp them with the time that they arrive. So at the end, we also will record and also timestamp what is the time that they leave the system. So that is the function of these record modules. So you just name it, and then statistics definition, double click, and then attribute, the same attribute that we use in our assign part A and also assign module. You have to type the same specific name. If it's capital letter A, then you have to again capital letter A. If it's a small letter T, you have to also put small letter T. If not, whatever you define here could not call what they are being created earlier. So this is exactly the same as sealer time. So what we assign as sealer time and arrive time, when we want to call this attribute, we have to name it the same. And then you just record the name again, and then do it for scrap parts, do it for salvage parts, and do it for ships parts. And then we are ready. And then you can start to run your simulation model. So we can just hit on the run button. So you can actually slide it whether you want to be extra fast or you want it to be slower. Let's run it again. Okay, slower. So we can see the parts. So since there are two different entities, it's best to create different entity picture for different parts. So it's easy for you to visualize which parts are currently moving in the simulation model. So you see in preparation B process, there's Q there. So this example is built using basic processes. Mostly are all in basic processes. So actually, depending on your creativity and your ability to explore further, you'll be able to explore even more modules. We even have more advanced modules. Whether to use it or not, depending on what kind of modules that you are developing, what kind of model you are developing, and how complicated you want your model to be. So you can always explore to try different kinds of modules if the basic modules is not capable in imitating the system that you are trying to simulate. And you see here, there are also small numbers here. These are actually the statistic accumulator, meaning that currently how many are in this process. So we have 1 is being processed, 2 is queuing, and then how many parts part A have arrived, how many part B have arrived, how many parts have been scrapped or salvaged or shipped. And then we have like how many fail and how many pass the sealer inspection. If you have any questions, don't be shy to ask. Or once you try it at your end and you have questions, you also can ask. So again, like we mentioned just now, even if you and your friends visit a factory or visit a system, and the model that you develop might be a bit different from the model that your friends develop, because developing a simulation model roughly or majority of time depends on your creativity, your experience, and how much of your understanding towards the actual system. So once it runs completely, and then it will pop up results where we can look at the results. And if you do not like to see this picture as a blue ball and a red ball, you can change it into a different picture. And of course, what we learned today is only developing the model logic. Arena is also capable in allowing us to develop the animation of this model logic. So like the example that we've seen early in the morning, where we talk about the differences between systems and model. So we look through a few simulation model. So all those things that we've seen are all the animation part of model logic. So when we present our model to the subject matter expert or people in the industry, sometimes this model logic, it's a bit hard for them to understand. So in order to help them to understand more, we usually build an animation. Then it's easier for them to understand the process rather than looking at these jargons. So with animation, we're able to show the movement of the entity, the journey of the entity. Let's say part A and part B, once it arrives, where do it goes, where do it move? So it's more visualized, more pleasant to be visualized as compared to us staring at this model logic. So let me accelerate. All right, so then you click on the yes, and then the report will come out, and then you can see the total number out. Total number out here, regardless it's scrap scrap, ship, or salvage. It's 625. And then we have all the waiting time of part A and part B. And then the total time of part A and part B is also here. And then we have, what else? Oh, we have this waiting time and total time for all the processes. We have 4 processes, preparation A process, prep B process, rework process, and sealer process. We have the average time, average waiting time for each of the processes. So if we want to improve our model, so you see here the average waiting time for rework process is 446 minutes, which is a huge time. So from this example here, we can say that rework is not so efficient because the waiting time, the parts have to wait for a long time before they can enter rework process. So this is how we know what part in the model for us to do some improvement. I see here the total time. So this is the waiting time. So this is the total time. Total time, each part spent in the rework is 497 minutes. So you can think of what is the best improvement or strategy that you want to try to reduce the waiting time in rework process. So you can come up with a few suggestions. What do you want to do to reduce? And then you test it in your simulation model. And then this is what we call as what if analysis. And then you try that new improvement, try it in your model, and then run it again and see whether the waiting time of the rework process is reduced or not. Because sometimes when we intervene with a strategy to improve certain process, in this case the rework process, we might able to reduce the waiting time of rework process, but with a trade-off of some other process. So maybe we able to reduce this waiting time here, and then the waiting time for other processes increases. So we need to look at that as well. So the good thing about simulation, like we said many times, is you can test over and over and over again in your simulation model, which is a safe environment. You test it until you are satisfied with the result. And once you get the most accurate or the best results, you can then implement it into the real operation. And then what else? You can look at all the values here and choose whichever suits you. And then we have the queue, or the waiting time. And then we have resources, the utilization of all the resources, how long they are busy. And then total number seized. How many parts being seized by all these processes. And then we also have, remember just now, we want to get the total cycle time of the parts from the moment they are created right till they are salvaged, scrapped, or shipped. So this is the output. So if we do not do the we did not use the record modules or did not use the assign modules to timestamp the parts, we will not get these results. So sometimes when we want results, something more than what is given by default, then we have to actually command Arena to do so. For example, is this. So once we have the record modules and also the timestamp, so you will get information like this. Okay. Any questions so far? Let's go back to our slide and see where are we. I think we covered this roughly. Okay. Oh yeah, we have not discussed this. Okay, so as mentioned, let's go back a little bit. Run. All right, so in the beginning, we mentioned that we want to run this model for 32 hours, 4 consecutive 8-hour shift. So we also need to make sure that this statement is set in our simulation model. So how to do that? We can go to run and then go to setup, and then you have something like this, and then you see we have replication length 32 for 8 hours shift consecutively. And then does it say it 1 hours? Yes, it 1 hours. It's stated they are required in hours, so you just put hours, and then 24 hours per day, then you have it, then you run. Right, so when you have this ready, again, like I mentioned just now, and I have to mention it many times, because some modeler do not go through the validation and verification process. As a simulation modeler, it is very important for you all to validate and verify your model. So let's say you are the one who are building this model. So you have to bring this model back to the factory and present it to the factory manager or operations manager, operations director, as long as the person who are very well versed with the operation of the factory, the process that you are simulating. You need to show them is the system description being accurately mimicked. Is all the processes as how it is in the actual system? And then you have the results generated from the simulation model, and then you show them their results and ask them if this result realistic or not, reasonable or not. And if they have their results, and then you have to compare their results and your results using some statistical tools. There are so many statistical tools to check the differences between two data. You can explore it later. And then once everything is good and it's in place, then only we can move to the next stage, which is to recommend improvement to the simulation model that you created. So just now, roughly, we look at the output. Rework process seems to be having some kind of bottleneck. So we can actually focus on finding a way to reduce the waiting time in the rework process. So you can come up with several interventions, try each of those interventions in the model, run it again, and then look at the similar performance measurement and then compare. So you don't come up with a new performance measurement. We have to compare different intervention strategy, different intervention processes using the same performance measurement. Only we are able to accurately decide which improvement is the best. So if you change your performance measurement or your output, then it's hard to actually decide which improvement is giving the best solution or the best result, right? I think before we end our class, I would like to show you some examples in Arena as well. After you guys downloaded the software, you can go to File and then Browse Examples. There are so many examples here that you can see which the model that has been developed by previous modeler using Arena. So you can look at airport security examples, assembly lines, bank kiosks, banking transaction, and many, many more. If we select one, there. So this one, they already developed the animation. So typically in a simulation model, because we are presenting this to the subject matter expert person, subject matter expert, so or public, so we need to have a description here. So this description is what we call as system description, the one that we discussed earlier, the one that we talk about the journey of the entity from the moment they are created right to the moment they are being disposed. So it includes which process do they go, and then each duration, the duration of each process, how many resources in one process. So you need to put it in the system description. And this is actually an animation, but we did not cover animation in our class. You only cover model logic. After you have the model logic, then you can build animation using the model logic. So when we present it to our subject matter expert, they can just look at the animation and see whether realistic or not the movement of the entity without need to look at the model logic. So let's run this model. So a good simulation model, a good animation needs to have labeling, because this is a hospital. We roughly, all of us has been to hospital, so we roughly can visualize what is what. That's the car dropping the patients at the hospital, and then the patients do some registration, and then they go to the ward. But if it's a system that is not familiar to the rest of the public, so it's good to do labeling, like what is it here? Is it a ward, or is it for an X-ray, or is it for a blood donation center, or what kind of process, or what kind of activities in the process? So we need to name it in detail. And also in simulation, apart from just building the model logic and also building this animation, we also can have some counter and graphs. So we can have, this is actually a clock showing the time of the current simulation run. And then we also have some utilization of all the resources here. And then the condition of this one they did not label it properly. So when they put it condition here, we are unsure whether this represents the condition of their patient or the condition of their processes, right? So if you are doing your animation, make sure you label it accordingly. We have some time. Let's look at the other examples. Let's see this. This one do not have animation. Let's look for a nice animation. This is an animation of helicopter combat. So the helicopter wants to simulate their mission if they to attack their enemy base. So let's run this. So they want to attack their enemy. So before implementing the attack strategy in the real situation, so they can do a simulation and see what is the best way to attack their enemy using their helicopter. So you see here, we have also some counter here where you know how many mission has been cancelled. And then what is the status of the current helicopter? How many have damage? How many have critical failure? And then the repair time. And then the replacement of the default parts, the inventory. So discrete event simulation, not only limited to industrial processes. If you can creatively think any situation that involve processes from one place to another another place, and then we have resources resources or queue in each of the processes, we can actually use discrete event simulation as long as it's not much on the high level strategy and strategies and policies. It's more on the operational level. You can actually consider to model it using discrete event simulation, just like the example of this helicopter combat mission. It is not similar with the typical industrial processes. Right, let's try one last model, one last example. We have pod model. This animation is a bit simplified. So we have the ships reaching the port. How to efficiently use the berth, available berth. And all the ships have to queue before they are given an empty slot. And the longer the ship queue, it costs a lot of money. So the port management can decide, given the large number of ship arrive, do they have to build another berth, or how can they improve the efficiency of the process here? So again, before we can build our simulation model, we have to do the model logic first. So once you have the model logic, once you validated your model logic, then you can do all the what if scenario, what if movement. And once you have your model logic verified, validated, then you can build your animation. So when you present the animation to your viewers, it's so much easier to understand as compared to asking them to look at this model logic. So this model logic is a bit like a mathematical jargon, which is hard for the viewers to visualize what is happening as compared to us presenting the animation to the viewers. All right. Any questions from students? I think we are at the end of the class. Let's see if we have any more. Done that. Okay, this one, but this one we already discussed earlier. If you want to change the entities picture, you can always go to the entity module. The entity module, which is where is the entity module? Okay, you can go to the basic process You just slide it and then you go to the basic process, go to entity, and then initial picture, you can change the picture to whatever picture that you want. And then when you run your simulation model, it will show the entity picture. I think we've done that. And so the takeaway from our second part of the class is we explored Arena. Arena is one of the many available software for discrete event simulation. So some students many of the students always confuse when I ask students, what types of simulation are you using? Many of them will answer Arena. So it's not Arena. Actually, Arena is the software that support discrete event simulation. So what is the type of simulation that we are using? It's actually discrete event simulation. So discrete event simulation, if we want to use the software, there are many types of software available. It can be Arena, it can be PowerSim, it can be FlexSim, many, but we are using Arena. So we need to alert that the type of simulation that we are learning today is called discrete event simulation. And also we look at how to build a very simple processes, which is the last end of the electronic parts assembly processes. And then we look at some simple modules, Arena modules. We look at create. The create modules is the modules that we use to create all the entities. And then we have process modules, is the modules that we use to capture all different processes in the system. And in these process modules, it's important for us to know what are the resources tied to this process, how many resources tied to the process, and how long does all these processes take place. And then we need to choose this cease, delay, release if you have resources or queue. If you do not have resources, you might change to select something else. And then we also learn to use the dispose module, where we need to dispose our entities once they already completed their journey. And then we have a decide modules, the one in the diamond, where it gives you a chance to split the pathway of your entity's journey. And then we also have the record modules, where you use to record whatever thing you want to record. And then we also have the assign module. So the assign modules actually is a very versatile module which you can use to assign many things. But in our example, we use the assign module to assign the sealer time and also the arrival time. And I think we also learn how to create change entity pictures. And we also see some of the examples of the animation from the Arena library. So if you are interested, you can go and explore all those libraries, and also you can check out a lot of videos in YouTube. If you are stuck in building your Arena model, you can always go and look for answers in YouTube, and also just Google. There are so many modelers that face the similar problems like yours previously, and they already found an answer, and then so they just create a short video on how they solve those issues. And also, if in cases where you try to run your simulation model and there's an error, usually Arena will help the modeler to locate where is the error. When you run, if there's an error, there is a pop-up message at the lower part of the screen, and then you click find, it will take you to the place where Arena thinks your potential error is. So Arena is actually a very user-friendly software. And once you learn how to use Arena, it will not be difficult for you to actually migrate to other different software, because all simulation software, regardless their their functionality, they always have that similar blank canvas, the blank canvas for us to do our simulation model. So again, I have to emphasize this again. When you do your simulation model, remember to validate and verify your model before you do your model improvement. If not, your model improvement may not be accurately representing the actual system. Right, so any questions? Finally, any questions from the floor? So I have this short exercise for you all to explore in your leisure time. You don't have to do now. You can do it at your end after you have installed the software. After we have gone through our class today, you can do this at your leisure. Try and see if you successfully built your model. If you guys do not have questions, then thank you so much for spending time for I think around 4 hours, 2 hours before lunch and 2 hours after lunch. So I hope all of you enjoy learning simulation, specifically discrete event simulation. So if you are interested to collaborate, you can always contact me via my email or also my LinkedIn. And if you want to talk more about other types of simulation like system dynamic or agent-based modeling or any analytics method, also feel free to drop me an email. So again, if there is no question for you guys, I think we are at the end of our class today. Thank you so much.
Professor,
Yes.
today on behalf of the Prince of Songkla University, we truly appreciate the wonderful lesson and advice. Once again, we would like to sincerely thank Professor for the special program and thank all the participants. We hope that everyone will continue to participate in our future projects. Thank you.
Thank you so much. Thank you so much. So see you all again in future.